Hello, welcome back. So this is part 2 of our missing data lecture, and we are going to play around in Stata and do an example of how to do some missing data estimation in Stata. And I'm going to focus on maximum likelihood and multiple imputation, and I have an example using a longitudinal / prospective cohort study. And we'll just kind of use that to highlight some of the techniques in this data that we have available to us. So I've written a do file, and here's what my do file looks like. And I thought I'd just do this interactively, and so you can actually see what I'm doing. And then this code will be posted called mi.do, and I will have the data set. It'll all be there, and so you can play around with it on your own. So the first thing let's do is let's just get our data set read in. So I'm going to use that PTSD data set. So here I've got the PTSD data set, and then I'm just going to create that 2-level combat exposure variable just to make life easier for us. So all here I'm doing is just reading in my data set and creating a dichotomous predictor for combat. And then let's just let me just show you a few of the variables, not all of them, but a few of them. So here's our data set, and you can see that it's currently in wide form. So I have 1 row per person, and I didn't show you all the variables that we've had. Remember, we have a bunch of variables here, but just to keep it all to fit in one nice little page. You can see we have a data set where we have a bunch of different variables that are mostly 0-1 predictors, and then I have a PTSD score called PCL time 1, PCL time 2, and PCL time 3. Same thing as the example that we used. And my total N down here is 2,950. You can see that I have baseline data for virtually everything. There's no missing data really on any of the data that was collected at time 1, but we have missing data for time 2 and even more missing data for time 3. So this is a great example of a data set where I have a longitudinal study design and I have missing data primarily driven by dropout or attrition, but there is some missing data on some of my baseline predictors. And for today, just to kind of keep everything simple, we'll probably ignore a lot of that because there just isn't that much of it. So we're going to really focus on what do we do when we've got missing data on our outcomes over time from study dropout. So the first thing we want to do is let's introduce the first MI in Stata has it's a big thing at this point. There's an entire reference manual just about MI, so you could spend a lot of time playing around with the MI suite of commands in Stata, and I recommend doing that. I'm just going to highlight probably 6 or 8 of them today that help me get up to speed and be able to do just a simple multiple imputation in Stata. The first thing we need to do is we need to set our data set. Again, same idea what we talked about before. Sometimes it helps if you do survival analysis, you got to tell Stata you've got a survival data set. If you want to do some of those repeated plots, which I showed this week, you got to tell Stata that, and it'll make things easier. So we have to set the data set to be able to do multiple imputation and then to be able to look at things. So under the mi set command, there's a bunch of different options. I know it seems counterintuitive because I have a wide data set, but this is the right option, F long, for the type of data set that I have here. So the first thing I do is I set my data set and tell Stata that in fact I have I want to do a multiple imputation, and notice that it added a few of these Stata variables here, these underscore mi variables. It added those to my thing. So that's all the feedback you get. It's basically set now to do multiple imputation. The first thing I like to do is the MI suite has some great things to be able to just look at your data and look at your data and how much missing is. That goes well beyond just a simple listing like what we did here. So I want to show you a couple of them. First is using the MI miss table. I want to do the summarize, and then I want to do patterns. So let's just do these one at a time. So let's do MI Miss Table summarize. And it gives you this great little table right here. And you can see that because I did the all command, it listed all of my variables. It shows us how many are missing, and then how many are greater than missing, and then how many are less than missing. In Stata, missing is the highest category, and so for us, all of our variables that have an actual number end up being below the missing one. So this is basically the number of missing on that variable, and this is the number that are not missing. So you can see we've got a data set with 2,950 individuals in it. So the ID has no missing variables, no missing values whatsoever, and they go from 1 to 3,000. Like I said, on our demographic baseline variables, we do have some missing data. So you can see I'm only missing 1 for race, which in this case, again, is white, not white. I have 8 missing on sex, which is female, not female, etc., etc. A little bit more missing on married and age. I'm going to ignore all this. So for the purposes of what we're going to do here, we're just gonna ignore that. If you were actually doing a multiple imputation, you would impute all of these things. But we're going to really focus on these two right here. We have no missing data on our PTSD score at time 1. That's great. We're missing 814 at time 2, and we're missing 1,664 at time 3. So our N goes from 2950 for time 1 PCL, 2136 at time 2, and 1286. So less than half. We're losing well over half by time 3, and our combat is like one of our baseline predictors. So we've got a lot of missing data. We're going to focus on our attrition over time, but we could easily incorporate the others. Second thing I want to show you is the patterns option, which is great. So again, let's just run that. So this shows you all the different missing data patterns in your data set. So remember in the lecture I talked a little bit about, do you have a monotone pattern or an arbitrary pattern? This is kind of getting at too, but it's really something I like to look at to see what's the nature of, if people are missing this, are they missing that, those types of things. Down here it lists what each column is. Notice that column 10 is PCL time 2, and column 11 is PCL time 3. So there are 1,008 people in our data set that are not missing any of these variables. The 1 means that they are not missing those. So 1,000 of our 2,950 have complete data on all 11 of these variables. Now 1,034, they have data on everything except 11, which is time 3. So we have 1,008 that have all 3 time points. We have 1,034 with everything and times 1 and 2 but not 3. And then 519 are missing 10 and 11, 2 and 3. So we have another 519 that have all the baseline and they're missing 2 and 3. And then you got to sneak in this other 228. They have it, they missed time 2, but they came back at time 3. So we do not have a once out, always out, right? So we do have some people, a fair number of people actually, who didn't respond to our survey at time 2, but we got them in our survey at time 3. So if we were to add these numbers up, 2,040, 2,560, 2,790, if my math is right. So out of our 2,900, 2,790 or so are really got everything for our demographics, but they're just missing our data over time. So that's why I'm just going to ignore all this stuff. But if you go down this, you can see, okay, there were 3 people who have this variable, missing this one, have these 2, and they're missing all of these. There's 4 people that have this. So you can see there's just a smattering of different patterns, and that's almost always how it works when you have a lot of variables. So it's a great procedure to be able to really get a sense of what's going on with my missing data. And again, in our case, we really want to focus mostly on what's going on up here and getting a handle on how many people are missing our different things. All right, so now that we've done that, First thing we really often need to do when we start talking about missing data estimation is we need to check that assumption. So remember, whether we use maximum likelihood or multiple imputation, we would like to be able to, the technique really requires us to be able to say that the missing at random assumption is reasonable. So we can't ever actually test it, we can never know for sure, but we really want to know, is it reasonable that the data are missing at random so that when I use this technique it's appropriate. The best way that I found to be able to inform whether I think that assumption is reasonable or not with longitudinal data is to look and first figure out who drops out and who doesn't and create a variable for that, and then let's compare those two groups on a bunch of our baseline data, which we do have. So I'm going to create a variable called miss, and they're going to be a 1 if they're missing either or both of PCL time 2 or 3, and they're going to be a 0 if they're not. So let's just run that, and then let's just do a little quick crosstab of that. So this. So now we see that missing 0 says that you are not missing time 2 or time 3 PCL. We got 1,045 people that fall into that category, 35% of our sample, and we've got 1,900, 65% of our sample in this missing category. So missing data is not trivial in this example. We have a lot of missing data, and in some ways a concerning amount, an overly concerning amount of missing data, right? So I don't like doing studies where my missing data goes above 15-20%, but this is a warts and all example. We've got 65% of our participants are missing data at time 2 or time 3 or both. So we got a lot of missing data. Now that I've created that, I can use that variable, which I called miss, to start comparing and saying, are the people who are missing different than the people who are not missing? So I did a whole bunch of tabs here. We don't have to do them all, but let's just look at one, for example. Here is gender. So these are the people who are not missing over time. Here are the people who fall out over time. I did the row percentages because I like to interpret it that way. So for the people who are not missing, they're about 9.8% of them are women. For the people who are missing, about 7.2. So men were more likely to drop out, and that's statistically significant. See that? So men were 90% of the people who stayed in, but they're almost 93% of the dropouts. So, and it's common. We see that pattern a lot. That depending on the topic, men or women might be slightly more likely. We have a white, not white. Again, we've got a mostly white sample. So we've got 2,400 versus 500. So we don't have a lot of non-white, and it's a heterogeneous. So it's wildly imperfect. But again, we see a pretty strong difference here. Whereas 9% of our people who stay in were not white, 21.5% of those who drop out, and that's significant. So we see a pretty big difference between white and non-white. So we got a whole bunch of these things we can look at. The one we really often care about, remember, is what does my outcome at time 1 look like? Do I see a difference in my outcome at time 1? A few of my variables are continuous, so the easier way to do the crosstab is using the table with the contents thing and then put in the mean. So let me just run this one right here. Let's throw them all together and I'll show you. So here, again, we're comparing those who stayed in the study and have all time points versus those who are missing. Are they different on education? The people who dropped out have a slightly lower, this is education in years. Younger, not uncommon to see that the younger folks are a little bit more likely to drop out. This though, this is the one I care a lot about. And this is actually great, right? Because what this is telling me is that the people who drop out actually don't look that different on our outcome versus those who stay in. A little bit higher PTSD score, but certainly not statistically significant. And by the way, I did run a t-test, and this is not statistically significantly different. The p is like 0.4. So this is great. So we know. So bottom line is we know there are some differences here on some of our demographic variables, but we can control for those in our model. So we can condition on those. And it's great to see that at least at baseline, it doesn't look like there are differences in our outcome between those who ultimately drop out and those who stay in. Now, that's no guarantee. That's no guarantee that the people who drop out of the study won't be the ones who develop PTSD. Maybe they didn't look any different at baseline, but a year later, a group of these soldiers develop PTSD symptoms or have an increase in PTSD symptoms, and they're less likely to come back and do the survey. So there's no guarantee that we're not going to see differences in our outcome over time. But at least it's kind of as good as we can do given the data, right? Since we can't test it correctly because we don't have the data. Second thing I do is I run a few regressions where I now start comparing. So here's that one where now I regress the PCL score at time 1 on missingness. So I just run that simple regression, and again, I don't see a big difference. I'm just re-expressing that. Actually, the P was 0.89, so no difference at all whatsoever. I can stratify that regression too. So for instance, I can do it. We know that the men were more likely to drop out than the women. So now I can say, let's look at the difference between the PCL scores stratified by men and women. So now I can say, was there a difference between those who dropped out and those who stayed in for just the men? There was not. Is there a difference for just the women? There is not. So again, that's a good sign, because what that's telling us that although we see a definite difference in the intercept, we see a definite difference in PCL scores and its missingness is related to men and women, we do not see differences for baseline. And again, I can do this for all these. I'm now going to jump ahead, and I'm going to get down to this one right here. Here's one that I often do, which is I actually take my binary outcome, my binary variable miss, not miss, and I regress that on a whole bunch of my variables. So now I took that and said, is that related to education age? This is really the big test of saying, how are the people who dropped out of my study similar or different than the people who stayed in? This is going to give us our most kind of best summary. And so all the P's that are less than 0.05 are differences, right? And this is a multivariate model, so it's adjusting for everything else. So they're the people who drop out, slightly different, lower education, younger, male, non-white, no difference on that, enlisted versus officers, reserve, so a lot of differences, but again, no difference on PTSD symptoms. So that's great. So it's there's an up and down side here. The upside, glass half full, is that it doesn't look like the people who drop out are any different on our outcome at baseline, and that's great. The downside is that they're definitely different, right? They're definitely younger, men, non-white, had a higher incidence of. So it's again, there's pluses and minuses, and this is a fairly dirty example, and hopefully you do this, and what you'll find out is that once I can, at least, even if you see a difference of your outcome at time 1, once you condition on some of these other things, then you want this one to go non-significant. And then any ones that are significant, we should put them in our model. And then that would hopefully say, we could argue that missing at random is maybe reasonable as long as we adjust for all of these different things. Okay? Now, so we've looked at our pattern of missingness. Let's now start jumping in and let's run some models. So I'm going to do two things here. I'm going to run some models using regular mixed, and I'm going to run some models, the same models, using the SEM approach. And I'm going to do this because I want to show you a slight difference between the two. So remember, I had mentioned earlier that when we're just doing a regular growth curve model, a random slopes model, that we can do that using mixed, but we can also do it using SEM. And there are some times when we want to do modeling things and SEM makes more sense. So I actually do a lot of growth curves using SEM because I want to leverage some of the other advantages of SEM. So for that reason, I want to show you, because the implications for how you deal with missing data are slightly different in the two. So let me first just show you the model that we're talking about here. And I'm going to show you that in mixed, and then I'll actually show you in SEM. This is the model that we're going to want to run. So the model that we're going to want to run is, I'm taking my outcome is, I create a long data set. My outcome is PTSD symptoms. I'm going to regress that on time, on combat exposure, and combat exposure by time. I don't have any of those other variables in there. I would. So I'm leaving them out of here just to keep everything simple. But you would put in female, you would put in enlisted, you would put in reserve. Remember, we found a number of these were related to PTSD over time, both intercept and growth. Those should all be in here. Just for illustration today, I'm going to keep it real simple and just bring in our primary exposure. People who experience combat, did they have higher symptoms of PTSD at baseline? That's the main effect. And did they increase or decrease more over time? That's the interaction with time. So this is the model that we're testing. We're fitting a random slope for time. I'm letting the intercept and the slope covary. And the reason I have new time there is that the time variables were not actually 1 year apart. They were 18 months and then 6 years. And so my old time variable, because I had PCL T1, T2, T3, when I did the reshape, it creates a time variable which is 1, 2, 3. I'm just going to make it 0, 1.5, and 6, because remember, I want my growth curve to be linear with respect to time. So when I'm doing a covariance pattern model, I treat waves categorically. I can use 1, 2, 3. Here I want to use actual time that's appropriate. And I also want the first one to be 0, because then my intercept is predicted PTSD at time 1. The value of the intercept will always be the when all the predictors are 0. So this is just a rescaling of time. Okay, with that said, let me first show you how we would do this using SEM. So here's a way to do a growth curve model in SEM. It's slightly different because what we now do is we say, let's pull out an intercept and slope from time 1, time 2, and time 3. You use these loadings to do your times. Then I say, regress the intercept and the slope on combat exposure. So intercept on combat, that's the main effect. Slope on combat is like the combat by new time here. So that's the same. Put an intercept in that model. And then, oh, by the way, you do some specifications. This is the covariance of the intercept and slope. That's here. And then let's do the variance. And here I set the variances to be equal, and we won't go into that in nitty-gritty detail. Notice right here, I use maximum likelihood as my estimation technique. When you do growth curves in SEM approach, you use the wide data set. We have the wide data set. We haven't done the reshape yet. You use a wide data set when you use SEM. That's one of the main differences when we do SEM, is that you don't use a long data set, you use a wide data set. So here's the rub. If you just specify ML, let me run this. If you just specify ML in SEM and do your growth curve, look at what your N does. It goes all the way down to 1042. And that's it throughout everybody who was missing on any of our variables. They were mainly people missing time 2 and time 3 PTSD, but there was also just a few missing combat exposure. So when you run a growth curve in SEM and you just pick maximum likelihood, you use listwise deletion. Mixed never does this. When you use mixed, it keeps all available data. So it never goes this low. So the reason I'm showing you this is that I can now get estimates for the effect of combat, the main effect of combat, the effect of combat over time. I can get the intercept for PTSD. I can get the slope for PTSD. I can get all the same variables out of this. Here's where I have the variance of my intercept, my variance of my slope, and the covariance of the two, because I let them covary. I get all the same variables, but it uses actually listwise deletion. So I can show you that, and we can compare that to some of the other techniques. And mixed will not do that because it uses a long data set. But here's what SEM will do. When you want to actually not use listwise deletion, but you want to use the maximum likelihood, you actually specify that you want to use maximum likelihood with missing values. So there's actually a different designation. If you just use ML here, you get listwise. If you want to use full information maximum likelihood under the SEM approach, you have to specify a different MLMB. So now let's run this one. Oops. Same exact model. And again, we get out our effective combat on intercept, our effective combat on slope, and all this. But now when we look at our N, it's 2,950. It used the maximum likelihood to retain everybody in your... So this is full information maximum likelihood, and it's using the likelihood for every person to keep them in there, and that becomes their outcome at time 2, and time 3 is their likelihood based on everything. Now, I didn't bring in all the other variables. So ideally, you would bring in, remember we had differences on female, male, we had differences on white, non-white, we had differences on age. Normally when I do this, you would want to bring all of those variables in because you would want to condition on those because those were the things that make the MAR assumption reasonable because we saw those differences. And I'm just doing it here because I don't know if the model will run if I bring in all those, frankly. So if you use SEM, you're stuck with basically listwise deletion if you use regular. If you want to use maximum likelihood and retain and do missing data, you have MLMB. You can also use multiple imputation in this, but I'm going to actually show you how to do that in mixed, but you can do it for SEM as well. So that's 2 ways of doing an SEM. Now let's actually do it in mixed, which is the way most of us would do it. So mixed does not do listwise deletion because it uses a long data set. It uses available data. So first thing we have to do, let's reshape our data set and let's make it from a wide data set to a long data set. Oh, now I remember something I did. Excuse me for that. I had done that setting it for here. So now I just wanted to undo that. Now let's try it. I don't know if that error with the log is going to be an issue or not. Yeah, it is going to be an issue. How do I do that? Okay. Sorry about that. Bear with me for just a second. Okay. Now let's do this. Let's make our data set long, and then let's create that new variable for time. Okay. So I basically have converted, I have a variable time still in there that's 1, 2, 3, but I have a new variable called new time. And then I can just run this model right here. So as far as we're concerned, we have a bunch of missing data, and we're just going to run mixed, and it's going to use available data to estimate that model, so we can see exactly what the numbers it's going to use are. So here, it shows that it has 2,936 groups. So it knows that, oh, by the way, you gave me an ID variable, which it calls its group variable, and I have 2,936, but it does not have 2,936 times 3, right? It is only using the full 2,900 at time 1, the 1,800 at time 2, and the 1,000 at time 3. So it's using this as its N, and it's using maximum likelihood. So it's using available. This one is going to look a lot like what FIML looks like under SEM. So this is where we find ourselves in this kind of weird gray area, is that if you just run mixed and the missingness is just on your outcome over time, then it will use your maximum likelihood to deal with it, and you didn't have to do anything. It didn't used to be this way, but that's the way it seems to be now. Okay, so this is like running available data in mixed, and it's like using the maximum likelihood estimator. Now let's talk about how to do multiple imputation in mixed. So first thing I'm going to do is I'm going to replace that data set, again mostly because I just want to there we go. So now I've got my replaced data set. So now let's create our combat exposure variable. Let's recreate that. Now here's what we have to do. If you want to do multiple imputation in mixed, you have to do a bunch of different things. First thing is we have to set it to long. Remember, I redid that, so I have to reset my thing and say, oh, by the way, this is an MI data set. You have to tell it the variables that you want to impute. So in this case, I only want to impute time 2 and time 3 PTSD. Even though I have missing in all these other ones, we're just going to ignore that right now. But normally, any variable that you have missing on, you can register and say, oh, by the way, impute all of these different things. So I'm only going to have it impute these two. Then I actually do the imputation. So the way you do that is you do MI and then use the impute. And then here is where you tell it what is the model that you want to use to impute. And this is where it's going to depend, is it a continuous outcome? Is it a binary outcome? Is it an ordinal outcome? And the options are things like logit, ologit, regress. You have a whole bunch of different things. You have some MC commands to do Bayesian stuff, some chained commands. There's a whole bunch of options under here. And frankly, I'm not sure what's better than, if this is better than that. The main thing that I have focused on is what's the distribution of my outcome? Should I be using a logistic? Should I be using an ordinal logistic? Should I be using a regular linear regression model? And do I want to use a Bayesian approach, or do I want to use more of a regression-based approach, a non-Bayesian approach? As I understand it, the MVN uses a multivariate normal, so it's assuming that these are multivariate normal, and it's using a Monte Carlo chain type thing. So that's what MVN uses. But like I said, there's probably 10 or 12 of them in there, and my recommendation is, depending on what it is you're imputing. And by the way, if I wanted to impute some of these other ones, I could pick, because these two are continuous, I pick MVN. I could also impute combat 01 and have that one be done using logistic. And I could do that all in one fell swoop, and you can look at the examples in this data. So MI impute, what model are you going to use, and then basically the outcomes, and then what you're going to use to predict them. So this is my imputers model. So notice that now I'm bringing in everything I have available to me. So even though I might only run a model down here that has combat, I'm going to throw everything in the kitchen sink I have to be able to impute what someone's PTSD score is at time 2 and time 3. And in a perfect world, you could have 20, 30, 40, 50 things here. Anything that you can use that you think will improve your ability to estimate and predict someone's score that's missing, you can throw in. I'm going to do 10 imputations, and this force thing is because some of these have missing data. And so the force will tell it to not worry so much about that. So I can just run this part. So yeah, so notice that it is using a Markov chain Monte Carlo way to do it. But it's doing multivariate normal regression. It did 10 imputations, and then it gives you some of that stuff since it's using the Monte Carlo about burn-ins and all that kinds of stuff. And basically it says, here's what I imputed, and you now have 2,950 values for time 2, and you have 2,950 values for time 3. And it did that 10 different times. Okay? And notice now over here, we start to have these variables that it creates. And then it's going to use those variables that it creates to allow us to do the analysis many times. So we still have a wide data set, right? So I never made it, even though I set it, and even though it includes long here, everything at this point is a wide data set. Now I need to flip it long because I want to use mixed for my analysis. So since I'm using mixed, I need a long data set. So I imputed with the wide data set, but now I got to make it long because I want to use mixed. You can't just use the reshape long. There's a special one for MI because we now have 10 stacked data sets in our data because it did 10 different imputations. So the N is not 8,800 or whatever, it's 88,000. So you got to use the MI. Everything else is the same. Reshape, long, the variable you want, all of the rest of it is the same. So just do the MI version of the reshape. So, as I talked about before, there are some steps involved to doing multiple imputation, but I will tell you they've made it much easier on us. So here's where it comes back and says, okay, for your data set, we're going to go from 2950 to 8850. And we got a variable called time, and these variables all go into a new variable. And then notice it did that 10 different times, and then it assembled them all together. So so it's a little putsy, but it does all the heavy lifting for you. Let's recreate that new time variable. And notice now that it's, again, I've got a big sample size here. Let's look over here. 97,000 observations because I stacked it 10 times. Actually, it's got 11 times in there. We won't go into that. Now, you did the imputation 10 times. You've prepped your data set. You're all ready to go. Here's how we actually do our model now. You say MI estimate with a colon, and then after that, you say this is the model I want to run. So this is the model telling Stata that you want to be able to do an analysis that uses imputed data. And then this is the model that I'm going to use. And notice, mixed, PCLT, regressed on time, combat by time, random slope for time, unstructured. Exactly the same. That part is exactly the same. That code does not change depending on whatever model you're running, linear regression, logistic, whatever model you're running, that stays the same, just this part. So let's run this. Now, unfortunately, here's the other kind of, not great part of a multiple imputation. It's going to take a while. So, number one, remember if you recall when I ran the model up here, just ran the regular unstructured model with 8,000 or 6,000. What did that take? It took maybe 20, 30 seconds. It wasn't immediate, right? Well, it's got to do that 10 times now. So even though you may have a fairly straightforward model and a reasonable N and something that doesn't take a lot of time, now it can start taking a lot of time because we have to run that model 10 times, and then it has to do a few other things in the background to combine those things and kick out a combined aggregate table. So it does it all for you. That's the great thing. It takes a little bit more time. Second, so it's got 10 different data sets that it's now running. What I sometimes will find is that if I've got a model that doesn't always want to converge well, it wouldn't be out of the question that not all 10 of your data sets converges. So remember, we imputed data for these two PCL scores, time 2 and time 3. I didn't tell it they all had to be positive, or I didn't put any constraints on it. It's not out of the question that suddenly you'll get an error saying there was a non-positive definite Hessian matrix, blah, blah, blah. And so one of the 10 won't run, or 2 of the 10 won't run. So particularly when we get into complex modeling, you're adding a whole nother layer of complexity, and you're having to run the model multiple times. And I will tell you, just to be completely upfront with you, part of the reason I'm only running it with my primary exposure, even though I would normally want to run it with all of those covariates because we know they're different, that model was choking a little bit. It was giving me fits, both here but also up here in the SEM part. So I just ran a simplified model for our illustration. But if we were actually doing this and we were going to write it up for publication, we need to have all those other covariates in here, and it'd be a tough model to get to run. I know I played around with it for a couple hours trying to see why it was choking and why it was not converging. So it's not It's not totally simple and it doesn't have its issues. Okay, so it ran. So the beauty is that, again, it's done most everything for us. So it's basically saying, I'm running this model. I did 10 imputations. I have 8,645 observations per imputed data set. That is our number times 3, right? So it is now doing it on our full data set that we imputed. We didn't impute combat, so we're missing a little bit of data there. And it gives us some information here that might or might not be relevant. The main thing is that it basically gives us our fixed effects table, and it gives us our random effects table, and these are aggregated over the 10 runs. So it had for every one of our 10 imputations, it got a main effect for time, it got a main effect for combat, and it got an interaction, and it got an coefficient and an error for each one, and it did all the averaging itself. And then what we're seeing here is just the overall. So the beauty is, if you decide to do this, you impute a certain number of times, 5 to 10 times. You figure out, you get comfortable with how you want to impute, make sure you're comfortable with it. And then when you actually go to run your model, you just have one set of results, and this can go in your table, in your paper. So that part of it is all seamless, and that's behind the scenes, and we don't have to deal with it. So that's great. One other thing I do want to, or a couple other things I want to show you. Can't use regular margins here. So because of the way this the imputation is working, each one of those runs got margins, and then I aggregated them, and so I can't use the regular margins command now, but there is a user written command called mi margins. You will need to install this, so you need to go out and find this, but I'm pretty sure we can just run this and it will calculate margins that are averaged over all of our things. So if you want to use margins, you can still use margins to help interpret your model, but you just can't use the regular. Oh, I'm sorry. That was my fault. I called this new time. Well, let's try this again. Okay, I don't know why that is, but this is what it's supposed to work, and I don't know why it didn't work. Maybe it's because I screwed it up somewhere up above or something. But just so you know, oh, maybe it's because I didn't put some factors on here or something. Maybe I needed to put eyes on there. Anyway, you can get margins from an imputed model. You just have to install this mi margins, and then again, you may have to play around with it. Okay, I want to show you one final thing, which is so we ran a bunch of models. We didn't take time. We didn't take time to look at the results, but I just made up this little table to show you a little bit of how these 4 different models we ran compare. So recall that for the first to do listwise deletion, I really had to do this in SEM, because unless I force mixed by actively throwing out people who don't have later data, they're going to use, its default is to use all available data. So I did this model using SEM. It had an N of 1042, and you can see I get an intercept and an effect for time, slope, a main effect, combat on intercept, and then combat on slope. And I get variance of my intercept, variance of my slope. Notice that when we move to any of the other 3, either the 2 that use maximum likelihood, mixed, SEM, or the imputed one, which we did in mixed, notice that the numbers slightly different. Like, let's look at this. This is the one that's in some ways most apparent. When we use listwise deletion, it estimated a 3.43. Everyone else estimated a lower regression coefficient. And the standard errors went from 0.48 to basically down to 0.2729 in any of the other 3. This standard error goes lower when we use appropriate. This standard error, notice the intercept actually went from 0.25 down to 0.14, 0.15. So again, when we just throw out everybody who's missing data over time, we probably see some bias in some of our estimates. Second, notice that whether we did it in mixed and didn't do anything. Remember, this is mixed without saying anything. This is just running what Stata does by default using maximum likelihood. It looks virtually identical to what SEM is doing when we say use maximum likelihood specifically to estimate missing values. So again, it appears that when you specify mixed and you only have missings in the outcome, that you will get virtually the identical answer whether you use maximum likelihood in mixed using available data or whether you do it in SEM and specifically tell it that you're using maximum likelihood to deal with missing data. So virtually the same answer. And then finally, when we did the full-blown multiple imputation, where we did 10 imputations and all of that, mostly the same answer, right? So a few little differences here and here. The combat by time interaction is the one that's most different in terms of especially the size of the regression coefficient, and the variances are a little bit different. This model is different though. Remember, when we imputed the values for this one, we used excuse me, combat, age, female, all of those things. If I had run these two models and adjusted them for those other things, we might have seen a little bit more agreement between these. So the big difference here might be that when we imputed the missing values, we took into account those differences that we know exist between men and women, white, non-white, younger and older. So the bottom line is you can do maximum likelihood, you can do multiple imputation. Maximum likelihood, when we use mixed, is pretty seamless. And even if you use SEM and you need to use some of the SEM techniques, it's pretty easy to make the SEM approach use maximum likelihood. Imputation adds a few extra steps, but not a crazy amount of extra steps. And again, nowadays it seems like with reviewers, it might be slightly easier to sell this idea that I imputed missing values and did that. Finally, I ignored the missing that existed on these covariates. I can only do that with multiple imputation. So the maximum likelihood, whether we're using FIML under SEM or whether we're using available data under mix, that only deals with missing on the outcome. So if you have a lot of missing on predictors, then definitely multiple imputation will allow you to impute those values and then include those. So that's the one instance where maybe multiple imputation gets a little bit of advantage, is that if you have a bunch of missing data on predictors as well as outcomes over time, you may lean toward multiple imputation. All right? Great.